So when learning how to build a computer, generally the first step that most people go through is learning binary numbers. And so that's what we're going to do here real quick. So binary is just another way of representing numbers. So humans, typically we use what's called base 10. So essentially in one digit you can have like 0, 1, 2, 3, all the way up to 9. And then once we reach 9, say we wanted to do 9 plus 1, that would give us 10. And if you notice, this digit and this digit are both in the ones place. We've added a new place here. We've added the tens place. And then that tens place has been set equal to 1. And so what we can notice here is that every digit as you go left is 10 times what the previous one. So if we were to take the number 500, we notice that this 0 is in the ones place, this 0 is in the tens place, and this 0 is in the hundreds place. And if the handwriting is bad, I'm using a mouse. It's not optimal. And wow. Okay. So we can represent 500 here as 5 groups of 100. So 5 groups of 100 plus 0 groups of 10. So 0 times 10 plus 0 groups of 1. So plus 0 groups of 1. And this would equal 500. It's a similar story in binary, except we only have two numbers. It's base 2, so we only have a 0 or a 1 per digit. And so what this means is that if we were to take a number, say 1, add 1 to it, we would do the same thing we did up here, except it would not be 10, but this would be 2. Because in binary, since the base is 2, that means that each digit you go left is 2 times the previous digits. So this is the ones place, this is the twos place, and then so on and so forth. It will just keep doubling as you go left. And so in a binary number, like 10110110, what way we can read this is the way I do it. I go right to left, and I assign a value to each of these. So this is the ones place, twos place, fours place, eights place, 16's place, 32's place, 64, and then finally 128. Usually, you'll see numbers written in this way. This is called an 8-bit number, and bit is essentially referring to a binary digit. So bit is kind of like a binary digit. And 8-bit numbers are generally used because this is the format of which a lot of letters on your keyboard are encoded. So like each letter on your So each letter in your keyboard has an 8-bit binary representation of it. So essentially, it's just a number that's assigned to each letter. But back to this, if we were to take this number here, we wanted to figure out what it was equal to in decimal, we would do the following thing. So we start right, and then if there is a 0 in the current digit, then we ignore that digit. So this one, we're not adding 0. We're not adding 1 here because this is a 0. And so we would go, why do I keep yawning? We go over 1. We look at this digit here. We notice that there is a 1, and this is the 2's place, so we add a 2. So we'll do 2 plus, and then we just keep going left. So we'll go left, and we'll see that this is a 1, so we're adding 4. We're not adding 8. We are adding 16. We are adding 32. we're not adding 64, but we are adding 128. And then you can just set this up like this: 128, 32, 16, 4, 2. Kind of go across and recognize this is 10. This is 10, that's 2, so the result is 22, 4, 7, 8, 182. This number in decimal. So the big takeaway here is to know that binary is just another way to represent numbers, except instead of using 10 unique values per digit, we're only using 2. And that's essentially it. So that's the first step in binary. So now what we're going to do is we're going to go over how a computer works on binary numbers. And the way that they operate on them is with logic gates. And I don't think there's a text tool in here anywhere. There is. So we can say that a logic gate is a we can just say an electronic circuit that has X number of inputs that, I guess we should say, that compares X number of inputs to give Y number of outputs. And this is a very general definition of a logic gate. So there are some logic gates that have 1 input, there's some logic gates that have 2 inputs, there's some logic gates that have 1,047 inputs. It just depends on what they're being used for. But generally they can be broken down into 2 types. So there is the single input logic gates, which I call SILG, for single input logic gate. And these are your buffer. I should be typing this, that'd be much easier for you guys to read. Okay. Let's try this over. So we have single input logic gates. And your buffer and your NOT gate. And then we've got a different type of logic gate, which is a multi-input logic gate. Which are your OR and XOR for the most part. And then there are other versions of this that we'll go over in a sec here. But these are essentially the 5 basic gates. We're going to start with a buffer. And a buffer is, when you ever see it drawn in a schematic, it would look something like this. It's like a triangle on a wire. And essentially a buffer just outputs whatever its input is. So if we have an input here and an output here, this is 0, this is going to be 0, and this is 1, this is going to be 1. Simple enough. And why am I yawning, dude? I don't. It's so weird. Whenever I try to record stuff, I just yawn profusely. I don't get it. But now that we got that, we can see that really this doesn't seem to hold very useful. But it actually is, more so in real life than in Minecraft, which is what we're going to be using to demonstrate in this series. We're going to be using Minecraft as a medium exploration, and then we'll move into things like Logisim so that we can get more sophisticated diagrams and circuits going. But a buffer in real life essentially is used for synchronization. So logic gates in real life, similarly to Minecraft, if you do not know, They have a little bit of delay, so it takes a little bit of time for these logic gates to compare and then output its to compare its inputs and then output. It takes a little bit of time, and so buffers are oftentimes used to just account for this time. You'll oftentimes see a buffer as an AND gate with its inputs tied. And I'll explain what an AND gate is later, but once I do, you'll understand why that is used. But generally, buffers are used as for timing. Sometimes they're used for controlling whether or not you want something to output. Some of them have another input here that controls whether or not this buffer outputs its input or not. But that's not exactly inside the scope of this video. So that's a buffer. And then the NOT gate is very similar to a buffer, and it's easy to get them mixed up. There's one key difference. They always start with a triangle, buffer and the NOT gate. So the NOT gate has this little bubble on the end, and whenever you see a bubble on the output or an input of a gate, it means to just invert it. So in this case, if we have a 0 here, this is going to output a 1, and vice versa. If this is a 1, this is going to output a 0. And so NOT gates are useful if you want things to turn on only if, say something is, say you turn on a switch, maybe you want that to only affect something if the switch is off. Or there's always a use for a NOT gate. NOT gates are oftentimes used in tandem with these guys here to create different types of logic circuits. But for the most part, these two gates are components of other gates that allow them to do more things. That leads us into multi-input logic gates, the OR, the AND, and the XOR. But one quick thing before we do so is I want to introduce you guys to a thing called a truth table. Now, a truth table is essentially a graphical representation of the behavior of a logic gate. So if I were to do one for an OR gate example, so I'll draw an OR gate above it. For this example, I'm using one with 2 inputs, but remember it can use any number of inputs. So an OR gate would look like this, if you saw it in the schematic. And we have to recognize that there are 2 inputs. A, that's a very ugly A, B. A and B are 2 separate inputs, and then its output will be Q. A little bit better there. Yep. So truth table for this thing, so the way you set it up is you go A, B, Q. And if we remember back to binary, well, the binary can be either a 0 or a 1. And so what we want to do is we want to list every output, every possible state that this OR gate can be in. And since we have 2 inputs, both with 2 states, that means that there are 4 different states, because 2 squared, which is how many combinations there are, is going to give us 4. So in this case, we know that A can either be off, and B can be off. A can be off, and B can be on. A can be on, and B can be off. Or A can be on, and B can be on. And the name of the gate, OR gate, gives us a pretty good clue as to what this gate will do. An OR gate will output if either of its inputs are on. So in this case, A or B. So if false or false, then we're going to output false. So we're going to give a 0. Here we're doing a 0 or 1, but since B is on, we're going to output a 1. The same is true for A. So A or 0, or 1 or 0, we have a 1, so we're going to output a 1. And then the same is true if both are on. And so this little truth table here will output every possible state of behavior that this OR gate can give us. And these are useful for down the road, because they can help you visualize the way a circuit's meant to behave. Used quite often, so I would say get used to these as soon as you can. Fiddle with them and practice with stuff, because you can make truth tables for really any circuit. You can make a truth table for an entire computer if you wanted to. It would just be very not constrenuous isn't a word. It would just be very tedious, not very useful because of the scale it would have to be at. But these are useful. It's pretty cool. You should get used to them. And so next thing we're going to do is this AND gate here. So an AND gate has, in this example, 2 inputs, but remember it can have more. And that's a very ugly thing. The AND gate will look something like this. So it looks pretty similar to an OR gate, except it has a flat back of it. In this case, it's got a curved back of it. And it has 2 inputs again, A and B, with 1 output, Q. And then we can construct a truth table to describe the behavior of this gate. So we have A, B, Q, and we do the same thing. So listing every combination. And hence the name AND. This will only output if A and B are both 1. And another word for something being 1 is being high. So if A and B are both high, then Q will be high. Otherwise, then it will be low. So 0 and 0 is going to equal 0. 0 and 1 is going to equal 0. 1 and 0 is going to equal 0. 1 and 1 is going to equal 1. So here we see, based on the truth table, that an AND gate will only output a 1 when both of its inputs are a 1. And this is very useful for using, like, in this example up here, when I said the buffer was an AND with its inputs tied together. So the way that that would be represented, okay. Oh, how to really move around a little bit. This is to add a note. No, it's okay. How do I get rid of that? Oh, okay. So what you'll see here, I'll delete this. What you'll see is that an AND gate with its inputs tied together, so like this. So what we've done is we've essentially made it so that A and B are connected. And we can really ignore the B column in this case. And since they're connected, we can also ignore this case, because if A and B are connected, then they can't be different. So this one has to be ignored. So we'll see that if A is 1, then the output is 1, and if A is 0, the output is 0. But yeah, that's an AND gate. They're pretty useful as well. They definitely make life easier when doing various things, like controlling the flow of data, similar to a tri-state buffer. Whereas where a tri-state buffer is used a lot in the, like on a physical breadboard, that's where they're used commonly, because electricity needs a complete loop to flow. Those are useful, so you can like cut off, you can like disconnect the output so it doesn't output to anything. Whereas an AND gate are more useful on the logic level, where you don't necessarily need a complete loop for something to work, like Minecraft Redstone doesn't need a complete loop to work. So this is useful. We're going to be using AND gates much more commonly than tri-state buffers, if at all. So that's the AND gate. Next is the XOR gate. And the XOR gate is a little bit complicated. It's kind of a combination of both this OR and the AND gate, but in a slightly different manner. So first thing is, in this case, it has 2 inputs, but do recognize it can have any number of inputs. And it looks very similar to an OR gate, except the only difference is, in the way you can tell easily, is that it's got this extra line here, which tells you it's an XOR gate, not just an OR gate. And the truth table for this, same setup as before. So we have 2 inputs. We have A and B, and then we have an output Q. and then we just list every possible combination of A and B. And then the and XOR gate stands for exclusive OR gate. And essentially what that means is that it'll output if A or B is on, but not if A and B is on. So if we look at the OR gate here, we'll see that it shares kind of this behavior, whereas if A or B is on, but it won't be on if both of them are on. So it might be easier to just fill this out. So follows a similar track that this does, except the only difference is where they're both on, this is off. And this has many uses. This can be used as a conditional inverter. So like if you were to denote that this B input were to be an like enable invert option, if B is always 1, then you can see that we get rid of this case and this case, and we also don't have control over B anymore. And so we'll see that if A is 0, Q is 1, and then if A is 1, Q is 0. And so we can use exclusive OR gates as conditional inverters. They have other uses, of course. Every gate has infinite uses, really. If you can find a way to integrate it, then it has its use. But that's just about it for these ones. The only thing we need to go over next is integrating the NOT gate with these guys. And I'll do that quickly over here. So we can use a NOT gate on the output of any of these gates to create their inverted counterparts. So an OR gate becomes a NOR gate, then an AND gate becomes a NAND gate, and an XOR gate does not become an XOR, it becomes an XNOR gate. And then a NOR gate is an AND gate, or an OR gate with that little bubble on the end of it. Because the bubble from the NOT gate is just put onto the end of the OR gate to make a NOR gate. And this guy's output is going to look something like this. So we got A, B, and Q, 0, 0, 1, 1, 0, 1, 0, 1. Then this guy is going to turn on only when both A and B are off. Otherwise, it will be off. Then the next one, and if you notice here, this is just the opposite of this. So if we were to invert these bits, we would get 1, 0, 0, 0, which is exactly what we have up here. And next is the NAND gate. So it's essentially this, except we add that little bubble on the end of it. A, B, Q, 0, 0, 1, 1, 0, 1, 0, 1. And then the NAND gate is the opposite of the AND gate's output. So here we have 1, 1, 1, 0. So in this case, a NAND gate will only turn off if both A and B are on. And something interesting about the NAND gate is that you can use any number of NAND gates to create any other gate you need, because essentially what you can do is you can take a NAND gate here, and if you invert its inputs like so, this has the same functionality as an OR gate. And so you'll see that here, this is just an OR gate. It behaves exactly the same. And the reason I'm even mentioning this is because if you wanted to build, say, a breadboard CPU like Ben Eater did, he oftentimes used NAND gates in tandem with each other, like in conjunction with each other, to create other logic gates. Because a NAND gate, with its inputs tied, similarly to the AND gate with its inputs tied, gives us functionality of a NOT gate. So we'll make a quick truth table here. 0, 0, 1, 1, 0, 1, 0, 1. We'll see here that since we don't have a B input, we can ignore the B column, and we can ignore all cases where A and B are different, since they're bound together and they can't be different. What we'll see here is that since they can't be different and we're going through an inverter, it will output the opposite of the input. So if the input is 0, output will be 1, and then these don't exist. And then if the input is a 1, the output is a 0. So there's always different ways of using these gates in conjunction with each other to give you other outputs or other behavior based on your needs. So that's the NAND gate, a little bit of a special one. NOR gate also kind of falls in this category, not so much. Typically when people refer to something called a universal gate, we're talking about the NAND gate. Sometimes they'll include the NOR gate, but usually the NAND gate is the one that's talked about the most. And so then that leads us to the XNOR gate, which is the XOR gate, but with an inverted output. So we make a quick truth table here, A, B, and Q. And then we just list every possible combination of A and B. And then we'll see that it's the opposite of an XOR gate. And what this means is that this XOR gate will output only if A and B are the same. And so if A and B are both zeros, then it outputs a 1, or if A and B are both 1, it outputs a 1, otherwise outputs a 0. And the XOR gate can be used to test to see whether or not two numbers are equal. So say you had, you wanted to see if the numbers 0, 1, 0, 0, and 1, 0, 0, 0 were equal. Intuitively, you can just see that this number here is worth more because the fourth digit is a 1, whereas here the third digit is a 1. So this one is, this higher order bit here is, it makes this one bigger. You can just see that intuitively, but intuitive thinking doesn't really translate over well to circuits, and so you need to kind of break it down and analyze why it is, and kind of go from there and figure out step by step how can we simplify the process so that a circuit can do it for us. And what you can notice here is we can kind of break this up into 4 different bits. We can do like bitwise operations, and that's what whenever you're breaking up numbers into individual bits like this, that's called a bitwise operation. So this will be 1 bitwise operation, and then the next one here, here, and here. And what we can do is we can use this XNOR gate to tell whether or not these two are the same. And since we can assign this A and this B, we can look if A is 0 and B is 1, then we get a 0. So they're not the same, so we know that they are greater, at least one is greater. And then using this, we can then use an AND gate with one of its inputs converted to test to see that. But that's also kind of outside the scope of this video. You can use, the thing I want you to take away is that the XOR gate can be used to test to see if two numbers are equal. So I'll give you an example that's more suited to that. So I'll do 1100 and 1100. Clearly we can see these two numbers are equal, but to an XNOR, but to a computer or to a circuit, it needs to be very explicit. And so here we'll start on the leftmost bit and go right. So here we'll look at where the case in the XOR truth table, where A is 1 and B is 1, A is 1 and B is 1. You see we get a 1, so this is true. for this bit is true. And then again, same case, 1 and 1, this is also true. And then where a is 0 and b is 0, we see we get a 1, so this is true, and then this is a duplicate. So now we can say here that a equals b. And those are just like very surface level applications of these gates. You can do a whole bunch of stuff with these gates, more than what I've explained. I encourage you to look into this on your own time outside of this, because if I were to do everything here, if I were to give you every single use for these gates, it would be a waste of both of our times, because we're not going to use every possible combination, but it is useful to know in certain scenarios how they can be used. Why do I keep yawning? I don't know. How they can be used to suit your needs. So yeah, that's basically it. That's the introduction. That's like the groundwork foundation, and from here we can build upon this. So yeah, so in this video you learned about binary and how to count in binary. Learned that it's just a different number system, and every digit as you go left is double the previous one. And you also learned about logic gates, how a logic gate is an electronic circuit that compares X number of inputs to give us Y number of outputs. In this case, we use 2 inputs and 1 output, but there can be more. And we went over a truth table, which is a visual representation of a logic gate's behavior. So I'll say thanks for watching, and make sure to keep going, because it's definitely worth it once you get it down and understand this stuff. I think it's really rewarding. I've certainly had a lot of fun learning about it. So yeah, that's gonna wrap it up. See you.